Okay, we're getting there, getting there. On page 8 here we have problems 29 through 32. Got some difficult problems. The first one is actually an easier one-step. Now be prepared, tomorrow there'll be a lot more of these one-step reactions here with a one-step transformation. And this one here is the Fischer reaction. Not going to do the whole mechanism for that. It's not quite necessary for this problem. The only thing we should know here is that this is made into a good leaving group, H2O, by adding the H2SO4, sulfuric acid, and it's going to leave and be replaced by this whole nucleophile right here. Right, and that is a substitution reaction on an acyl group, so A is the only one showing that. The OR group here has replaced the OH group with a catalyst. Okay, number 30 here is a longer drawn out problem here. This is a full retrosynthesis one, a longer one involving benzene. And you can see we start with benzene. Now we've added one carbon on this side, and then an amine compound as a functional group and a bromine functional group. We also observe here that these are para to each other, which means that we had a para group on there before the second group came on. So the para, we got orthopara, of course, directors. The bromine here is a orthopara director. Carbon now in this form is also an orthopara director. So it depends on when that bromine was added. And this here looks kind of confusing, but that is a reduced form of a CN. Now you may not know that, and you may have to just refer to the answer choices. That is one carbon that was added, and we can look through, and a nitrogen. We can look through our list of reagents and see if we can find that one carbon. Here we have it. Here we have it. Here we have it. We go to answer choice D. In this case, benzene gave you a break, and we can eliminate that one. So we have 3 answer choices. And let's see here. The next thing we want to look at here is our list of reagents here, just kind of getting a grasp of those. And this one, these two right here, we do have the bromine, which is added first. So that would put a BR on there. I'm sorry, I'm going to put it right there. But whenever we carry out our next reaction right here, whatever that may be, it's going to end up going to that para position right there. So that's a possibility. We look at C right here, and C is a reagent. This one you just have to know, this is a reagent that reacts with NH2 to make it N2. That right there, there's no NH2 on this ring, but hopefully you will know that this does not add an NO2 to the ring. It is the nitric acid that adds an NO2 to the ring. And we have to decide if we need that, but C is now eliminated based on that. We can further look down the list here to see if we can find anything else that's kind of crazy looking. It looks like NO2 was added twice. Here, this reagent here is the reagent used to make a cyclopropane ring. Here, the thingamajigger right there. And let's see here, what else? And that's pretty much it for C as far as eliminating C. So it always comes down to two answer choices though. And let's see here. With A, we can work this out, try to work it out. Here, we're going to have to refer to our nucleophile electrophile theory with A. If we just add CN to this, the only thing CN could possibly do is some kind of nucleophilic reaction here. All right, and that would be a reaction that puts a negative charge in the ring. That is not what is going to occur right here. We're not going to carry out that type of reaction. We want to put something in the pair position. So at this point you could eliminate A because it doesn't add the right reagents. So the only thing that's going to put a CN on there is this nitric acid method, where this is how you get an N onto the ring to do a diazonium salt. So let me show you this. What we're going to do is add nitric acid with some sulfuric acid. That puts the NO2 on that pair position. Then we're going to carry out some kind of reduction right here. Have to reduce it to convert it to a diazonium. Let's see what's in this list right here. We have iron. So we can have iron, or we can also have tin, though it's not stated in there, with some HCl. That reduces the NO2. Reduces means we add H's like this. That now can be converted to an N2. You see that's converted to an N2 using this NaNO2, the sodium nitrite it's called. So that's sodium nitrite, usually with HCl and cold temperatures, 0 degrees Celsius. This is a salt, so you can put an N plus right there, and sometimes the chloride gets shown. This is kind of, who cares about the chloride right there. But the diazonium is also a nucleophilic reaction where we can replace it with certain nucleophiles. Here are the CN. And let's see. This is copper cyanide, slightly different reagent used in this case. Copper is totally something that can be ignored because we're going to add the CN nucleophile in place of the N2. So this is literally like an N2 leaving group right here. It leaves from the benzene. Okay, and then you see that that's what I stated here in this problem. CN was going to come in at some point, but you can see it's in reduced form. I'm not even going to do those last two steps. CN can be reduced to an amine compound using the lithium aluminum hydride. Okay, the next one's here. Number 31 is going to be a quick one because you can see this is the phthalimide problem. Phthalimide here replaces the bromine here with a nitrogen. That is the source of the nitrogen. It becomes NH2, and we just have to find the correct answer choice, which I believe is D in this case. 32, a little bit more complicated. This is where we add two methyl groups. What we went over today on the April 10th. Here we add two methyl groups to this, and it becomes positively charged, so it becomes a leaving group. Here's the alpha position on one side, the alpha position on the other side. Those were selected so we can find the betas. There's the beta position, there's beta position, there's beta position there. Well, the thing to know with this elimination here is that we get the Hofmann The Hoffman here is the least substituted double bond, in contrast to the Zaitsev, which is the most substituted. So least substituted means we also have to find the least hindered. The least hindered side is this methyl group right here. So let me do this with the redraw method on this same sheet of paper here. When we redraw this here, we'll want to draw a double bond right here. All right, but before we do that here, or after we do that, it doesn't matter. This is the leaving group that's leaving. A leaving group means a bond is breaking at the carbon that's being transformed, this one right here. So there's the answer choice. We can actually number this to make a nice linear chain, 1, 2, 3, 4, 5 in our zigzag format. Attach a nitrogen to the end of that. And let's not forget about our double bond there between carbons number 1 and 2. Okay, you see that? There's the answer to that one. Here is the mechanism. Let me show you briefly. If we had a hydrogen right here, the OH is going to come along. I know this is kind of getting muddled here. OH is going to come along. We form a double bond, and then that leaving group leaves, but it basically means that bond is breaking. That nitrogen is staying attached to that side of the molecule. So our only answer choice here that could be is C.